All right, so before we get into this lesson, I want you to think about what these three people have in common. If you said predicting, you are correct. So while the fortune teller doesn't have much scientific data to back up her predictions of the future, the meteorologist and the now well-known Dr. Fauci use evidence to either predict what the weather will be like for the week ahead or to predict the spread or casualties due to dangerous diseases. For today's lesson, you will be doing some predictions of your own. These are going to be based on the types of reactions we recently learned about. Okay, so our learning objective today is I can predict the product of a reaction given the reactants. Okay, so before you can predict the products of a reaction, you have to determine the type of reaction that is taking place. So we previously did this by looking at an entire equation, but now we're just going to be given the reactants. Recall the 5 types of reactions: synthesis, decomposition, single replacement, double replacement, and combustion. I'll take you through some examples for each of these types of reactions to help you acquire the skill of predicting products. Okay, so the first one we're going to talk about today is predicting synthesis reactions. So this is when we have 2 reactants combining to form a compound. Now, these reactants could be elements or they could be compounds. So I could have 2 elements coming together. I could have an element and a compound coming together. And in very rare cases, I might even have 2 compounds coming together. But this synthesis reaction is only going to have one product. So it'll always have one product. All right, and to keep it simple for us, we are only going to be using elements to predict. So if you see 2 elements in the reactants, it is going to be a synthesis reaction, and we're going to create one product from those 2 elements. Okay, so for a lot of these, you're going to probably have a metal and a non-metal, and you should know at this point that means that you are going to be creating an ionic compound. Now, with ionic compounds, remember that you have to think about charges. So you have to think about charges before you just shove the element symbols together. So if I'm looking at example 1, I have zinc reacting with fluorine. So zinc, I know, has a +2 charge on it. Fluorine, all right, so this is a diatomic element, so you can see that 2 here. Fluorine's ion is F, and it only has a -1 charge. So this is zinc with a +2 charge. This is F with a -1 charge. When I put these together in my compound, I am not going to be concerned with any of the subscripts. So like these things, I'm not concerned with that when I'm putting these 2 ions together. All I'm concerned about is your ions and your ion charges. So here I have zinc with a +2 charge. I have fluorine with a -1 charge. I know that does not cancel out to 0, so I'm going to have to do my crossing and dropping. So if I have zinc reacting with fluorine, it's going to create zinc fluoride, and that 1 technically would cross down after the zinc, the 2 crosses down after the fluorine. And the last thing I'm going to do is just check and make sure that it's balanced. So I wrote out the formulas correctly. Now I have to check to make sure it's balanced. All right, on both sides, it looks like I have 1 zinc atom, and on both sides, it looks like I have 2 fluorine atoms. So this is already balanced for us. Okay, so example 1 was given to you in that skeleton formula or the formula equation. For example 2, we are given words. So that means that we're going to have to complete the word equation, and then from there, we're going to have to write out the actual equation. So here, I have lithium and phosphorus. So right off the bat, once again, I have a metal and I have a non-metal. So I know I'm going to be creating an ionic compound. So with our naming rules, remember that with naming, the metal is going to stay the same. So it's just going to be lithium. I'm going to check my periodic table to make sure lithium only has 1 charge, which it does. And then remember that our nonmetal is going to change to the IDE ending. So this would be lithium phosphide. So remember that phosphorus is one of those weird ones. All right, so lithium and phosphorus are going to react to create lithium phosphide. All right, now I have to go ahead and write in my formulas to make my skeleton or my formula equation. So lithium is a metal. I just write the symbol for metals. I'm going to put that in front just in case I have to balance it. Put that in front of there. Phosphorus is a nonmetal. Now remember, with nonmetals, some of them are diatomic. In this case, phosphorus, if you look on your periodic table, it's not one of those diatomic elements, so I'm just going to leave it as a P. All right, now when I make this ionic compound here, remember that you have to think about the charges for each ion. So lithium has a +1 charge, phosphorus has a -3 charge. So once again, my charges are not balancing out. I'm going to have to cross and drop to get lithium. I have 3 of them, and then 1 phosphorus atom. I almost forgot to do that. All right, the last thing you're going to do is make sure that this is balanced. So just looking at our equation here, all right, I have 1 lithium here, but over here I have 3 of them. So I'm going to start with my metal first. To balance it out, I'm going to have to multiply lithium over here by 3. When I do that, it's not affecting anything else. It looks like I have 1 phosphorus on both sides, so now this is a balanced chemical equation. One thing that I do want to note is that a lot of times people aren't writing these in when they are writing the formulas. This is really important. This is what I expect of you. This will help you not make mistakes in the future. So make sure that if you have an ionic compound, you are writing the charges of your ions. All right, the next one we're going to talk about is predicting decomposition reactions. So remember that decomposition is when you have a reactant breaking down into 2 or more simpler products. Now, these simpler products could be a couple elements, it could be an element in a compound, or it could be a couple simple compounds. All right, and once again, to keep it simple, we are going to be using binary compounds as our reactant, which means that these reactants are going to be broken down into the elements that make them up. So for decomposition reactions, one way you can tell that it is a decomposition reaction is when it only has 1 reactant. So anytime there's just one thing on the left side of the arrow, or 1 reactant, one thing that you're starting with, it is going to be a decomposition reaction. All right, let's try some examples. So for this example, I have ammonia, which is NH3. When I talk about decomposition, I'm just thinking about the different elements that this is going to be breaking up into. So this one's pretty easy. So I know that it's going to break up into nitrogen, and it's also going to break up into hydrogen. The only thing that you have to keep in mind is how you write the formulas for each of these individual elements. So remember that you have diatomic elements that have to have that 2 subscript with them. So both nitrogen and hydrogen in this case are actually diatomic elements. All right, last thing we're going to do now is balance it. So this ammonia split up into nitrogen and it split up into hydrogen. Now we got to balance it. So just looking here, I see that my hydrogens are really going to be out of whack if I don't figure out what my least common multiple is for those. So I know that 3 and 2 both go into 6. So I'm going to try to get my hydrogens to 6 right away. I'd have to put a 3 here. Remember that your coefficient multiplies your subscript. And over here, I would have to put a 2. All right, so here, when I did that, my hydrogens balanced out. And by putting that 2 in front of my ammonia here, I'm also balancing out the nitrogens on both sides. The next example, once again, is giving you the word equation that you have to write out the words and then write the formula or skeleton equation and then balance it. So we'll do this example all together. The first one that we have here is chromium 3 sulfide. All right, so chromium 3 sulfide is going to split up into 2 different elements. It's going to split up into chromium, and it's going to split up into sulfur. So it's going to split up into chromium and sulfur. So those are going to be our products that we are going to be creating from chromium sulfide. All right. For writing the formula for chromium 3 sulfide, remember that the Roman numerals tell us what the charge on chromium is. So I know this is chromium +3. I'm going to look at my periodic table, and I'm going to look up the charge for sulfur, which is -2. All right, these do not equal 0, so I'm going to have to do some crossing and dropping. So it's going to be Cr2S3. Put that in front of there in case I have to balance it. And then chromium is just Cr. It's a metal. Remember, metals, we just write the element symbol for it. And then sulfur is a nonmetal, but it is not one of those diatomic elements, so I don't have to worry about putting my 2 subscript on it. All right, from here now I have my formula written correctly, just have to make sure that it is balanced. So if I have chromium, I have 2 of them on the left side, I'm going to have 2 of them on the right side. If I have 3 sulfurs on the left side, I'm going to have 3 on the right side. All right, so picking up with predicting single replacement reactions. Remember that this is when we have an element replacing another in a compound. So typically your metals are going to replace the cation and your nonmetals will replace the anion. So that's really what you got to look at first. Is your singleton, or that single element that's off by itself in the reactants, is that going to be a metal or a nonmetal? Keep in mind that with predicting single replacement reactions, it's always going to be those ones that have one element and one compound in the reactants. And those are actually going to just be rearranged in the products. So working on some examples with predicting single replacement reactions. So our first example gives us the skeleton equation. I have calcium reacting with lithium chloride. So I'm going to look at this singleton guy over here and I'm going to determine, is it a metal or a nonmetal? I know that calcium is a metal, it's a cation, so it is going to be replacing the metal in the lithium chloride. All right, so lithium is the metal in that one. I know that calcium is going to be replacing lithium. So when I make calcium bond with chlorine, so when these 2 bond with each other, I cannot just shove the symbols together. These are ions. You have to think about the ionic charges. So I know that calcium has a +2 charge and chlorine has a -1 charge. So when I make the formula for calcium chloride, I look at my charges, they don't equal 0, I'm going to have to cross and drop. So it would be calcium and then chloride with a 2 next to it. All right. Last but not least, since calcium now bonds with chlorine, it's going to kick lithium out. So lithium, remember, is a metal. All we do is write the element symbol to show that he's off by himself. From here, last step, we need to balance it. So I'm going to look at my metal first. So I have 1 calcium over on the left side, 1 calcium on the right side. That's good. Lithiums, I have 1 on the left, 1 on the right. The only thing is here, chlorine on the left, I have 1, and on the right, I have 2. So in order to make it 2 chlorines on the left side, I'm going to have a 2 coefficient in front. When I do that, it also, remember, affects that lithium here. So now I have 2 lithium on the left. I'm going to have to balance that out with 2 lithium on the right. All right, the second example is going to be iodine, and it's going to be reacting with potassium sulfide. So when iodine reacts with potassium sulfide, so I'm actually going to write out the reactants part first because I think it might help. So iodine, all right, iodine is one of those diatomic elements. So remember that you had to memorize those diatomic elements. Iodine is one of them. I have to put a 2 subscript next to it because in nature it does not exist on its own. It's always bonded to at least another iodine ion. All right, potassium sulfide is an ionic compound. Potassium has a charge of +1. Sulfur has a charge of -2. All right, so these do not equal 0. I'm going to have to do my crisscross or cross and drop. All right, so K2S. All right, now I'm going to look at this singleton over here, and I'm going to determine, is that a metal or non-metal? So I know that iodine, since it's on the right side of the periodic table, is going to be a non-metal. So that means that it's going to be an anion. Sorry about that. An anion. All right, so that needs to replace the anion in this compound. So the anion, the one that's got a negative charge, as we said up here, is going to be sulfur. So I know that iodine over here is going to kick sulfur out. All right, so I'm just going to kick sulfur out. And it is going to replace sulfur and bond with potassium. So in order for iodine to bond with potassium, I have to know the charges. All right, potassium we already said had a +1 charge. Iodine is going to have a -1 charge. So when potassium and iodine bond with each other, it's going to create potassium iodide. Keep in mind that when you're writing the formula, the metal always comes first. So even though like the way that this one's written, some people might think iodide comes first, it does not. So potassium comes first, iodide comes afterwards. Both of these are going to cancel out to be 0, so all I do is write Ki to show those two atoms bonding together. All right, so I kind of skipped through writing the name for this because I think it's easier to write out my symbols and then kind of go back to the name. So here we said that sulfur was getting kicked out. All right, and we just talked about how potassium is bonding with iodine to create potassium, which only has one possible charge, iodide. Okay, the last step is to balance my equation. So if I look, it looks like I have 1 iodine on the right side and 2 on the left. So I want to balance out those iodides right away. And then when I do that, this 2 is affecting the potassium here. So now I have 2 potassiums on the right, and I also have these 2 potassiums on the left that balance out. I have 1 sulfur on each side, so now this is a balanced chemical equation. I don't want to forget to mention, sometimes with compounds, you might have hydrogen that will act as an ion. So hydrogen has a +1 charge. It's one of those elements. It's not a metal, but sometimes it acts like a metal. So that's kind of why it's positioned where it is on the periodic table as well. Okay, so with predicting double replacement reactions, remember that these are when we have 2 compounds exchanging ions to form new compounds. So they're either going to switch up their cations or they're going to switch up their anions. Either way, we're going to have 2 new compounds in the product. So there's always going to be 2 ionic compounds in the reactant side. So what I'm starting with, they're going to switch partners to make 2 new ionic compound products. Okay, so for the first example, and I'm just going to preface this and say that anytime with a double replacement reaction, I am going to write out the charges of my ions. So if I have calcium chloride reacting with lithium sulfide, all right, I know that calcium has a +2 charge. I know that chlorine, remember I'm ignoring this 2 here for now. I know that the chlorine ion has a -1 charge. Lithium, if I look at my periodic table, has a +1 charge. Sulfur has a -2 charge. Okay, so for this example, now calcium is going to bond with sulfur and lithium is going to bond with chlorine. So all I'm doing is looking at the charges and determining how to write the formulas. So for the first one, let's just say calcium sulfide is going to come first. So I'm going to have calcium that has a +2 charge and sulfur that has a -2 charge. So since these canceled out to have that net charge of 0, I am not going to write any subscripts with that formula. All right, lithium chloride, once again, I have a +1 charge and a -1 charge, so they're going to cancel each other out. When I write the formula for lithium chloride, remember that you're basically just starting here. All right, you're not paying attention to these subscripts, okay? We only pay attention to those subscripts when we're balancing. So here I'm looking at my +1 and my -1. They're going to cancel each other out, so I'm just going to write LiCl. All right, last step, I need to balance this. All right, got rid of some of that messy stuff. So now to balance it, it looks like I have 1 calcium on both sides. My chlorines, all right, I have 2 on the left side, and I have 1 on the right side. So to balance that out, I'm going to put a 2 on the right side. When I do that, remember that 2 also applies to the lithium. So now I have 2 lithiums on the right side. I need to balance it out on the left side, which it looks like it already has 2 on the left side. So that one's balanced. Last but not least, sulfur. It looks like I have 1 sulfur on the left side and 1 sulfur on the right side. So that's balanced as well. Now it is a balanced chemical equation. All right, for example 2, once again, we're doing the names. We have to go to the skeleton formula and then balance it. So remember that with the names, the metal is always going to come first. So I know that sodium and magnesium are my metals. I'm going to write my ions above each of these. So sodium has a +1 charge. All right, magnesium has a +2 charge. All right, my anions in this case, nitrate. So remember when it ends in 8, it's going to be on the back of your periodic table. So nitrate is going to be NO3, and that has a -1 charge. And then bromide is just bromine, and that's going to have a -1 charge. So my sodium, my metal from this compound, is now going to bond with the anion or the bromine from this compound, and my magnesium is going to bond with my nitrate. When you are writing out the names, remember that the metal comes first. So you can start with either one. I'll just start with sodium bromide. All right, and then I'm going to have magnesium nitrate. All right, so both of these only had 1 possible charge, the sodium and the magnesium. If you have an element that has more than 1 possible charge, you need to see what that charge is in the reactants. It's going to be the same in the products. Okay, now I have to make my formulas. So +1 and -1, that cancels out. Remember that this 3 is part of nitrate, so it's got to stay with it. But I'm basically just getting rid of these charges. So sodium nitrate, put a line in front of there. All right, magnesium bromide here, this does not equal 0, so I'm going to have to do some cross and drop action here. So MgBr2. All right, sodium bromide. So sodium had a +1 charge, bromine had a -1 charge. All right, so it's going to just be NaBr because those charges cancel. And then magnesium nitrate. So magnesium had a +2 charge, nitrate had a -1 charge. So that will be, I'm running out of room here, MgNO3. And since nitrate is a polyatomic ion and has to stay together, that 2 from my magnesium, when I do my crisscrossing here, my 2 from my magnesium is going to have to apply to that whole nitrate. So it's going to be 2 nitrate ions in that formula. Okay, so we have it written out correctly. The last step is to make sure that it is balanced. So let's start with the metals. So sodium, I have 1 on the left, 1 on the right. Magnesium, 1 on the left, 1 on the right. I also always do like to start off with my polyatomics. I think it's just easiest to spot those. So looking at my polyatomic here, I have 2 groups of this NO3. So I have 2 groups of it over here, but over here I only have 1, right? Because I don't have a separate subscript for that NO3. So this means that I only have 1 NO3 on the left, but I have 2 on the right. So to balance it, I'm going to have to put a coefficient in front of my sodium nitrate. When I do that, now it's changing how many sodiums I have. So I have to make sure that I am changing that on the other side. So now I have 2 sodiums here. I need to make sure that I have 2 sodiums on the right side. When I do that, it's going to change how many bromines I have. So now I have 2 bromines on the right side, and lucky for us, that's going to actually match up with the bromine on the left side. Last check, I don't know if I did magnesium yet, but I have 1 magnesium on the left, 1 magnesium on the right. It is balanced. Okay, so for a combustion reaction, so this is when a hydrocarbon burns an oxygen. It's going to give off intense heat and intense light. along with the products. So I didn't put the products in here up top, but the products are always going to be CO2 and H2O. So this is going to be really easy as long as you can recognize what your reactants are. So a hydrocarbon, remember, is when you have a substance that has hydrogen and carbon. Sometimes this substance can also contain oxygen. So if you see one with oxygen, don't rule it out as not being a hydrocarbon. So for our first example, we have methane or CH4 reacting with oxygen. I know, as we just said here, right here, the products are always going to be CO2 and H2O. So CO2 and H2O. All right, last thing that I need to do now is balance it. So that's probably the hardest part for these combustion reactions. Remember my tips. I say that if I have hydrogen, I'm going to look there first. If I have a subscript of 4, if I divide that by 2, it gives me an even number. So that tells me that I'm probably not going to have to multiply all of this by 2 for coefficients. So I'm going to start with my carbons and hydrogens. Carbon, it looks like I have 1 on each side right now, which is awesome. Hydrogen, I have 4 on the left. I only have 2 over here, so I'm going to have a 2 coefficient in front of there. All right, I know that I want to leave my CO2, so my carbons are matching on both sides. I'm going to count up my oxygens on the right side. So I have 2 here, and I also have another 2 here. So over here I have 4 hydrogens on the right side. 4 oxygens on the right side. And I have to make that balance on the left side, which only has 2 currently. So to make it 4, I would put a 2 coefficient in front of that. All right, the next example, so as I said, sometimes oxygen is contained in there. When it has this OH group, that's called an alcohol. That is still a hydrocarbon though. So alcohol does combust when it is burning in oxygen. All right, so once again, my products are CO2 and H2O. All right, this one can get a little tricky. Okay, so since I have hydrogens in a bunch of different places, which I usually don't, I'm going to start with the hydrogen. So one thing that I notice is on the left side, I have 4 plus 1 hydrogen. I have 5 hydrogens. That's not really going to mesh with the 2 hydrogens over here. So I have an even number over here. I have an odd number over here. I do not like that. I'm going to have to somehow make the hydrogens on the left an even number. So if I multiply 5 by 2, that's going to give me 10 hydrogens, which is an even number. So we're going to try that. So if I put that 2 there, now I'm going to have 10 hydrogens on the left. And when I try to make that 10 hydrogens on the right, I would have to put a 5 here. And just like we've talked about in a lot of the combustion balancing equations, when I put that 5 there, it's actually making my oxygens now an odd number, which isn't going to work because over here it is going to be, on the left side, it's going to be even. So that tells me that like the trick to this is basically multiply it again by 2. So I'm going to completely kind of start over here. All right, so instead of 2, I'm going to make this 4. All right, now if I do that, I'm going to have, let's see, I had 5 hydrogens. I'm going to have 20 hydrogens. So to make it 20 hydrogens on this side, I'm going to have to make this a 10. All right, I do have to balance my carbons. They are not balanced yet, so remember hydrogens and carbons first. Here I have 4 times 2, which is 8 carbons. I have to balance that out on this side, so I'll put an 8 coefficient in front of it because carbon, I only had 1 since it doesn't have a subscript next to it. All right, now I need to add up all of my hydrogens on the right side. So here I have 16 plus 10 more. All right, so 16 plus 10 is going to be 26. All right, over here, let's see with oxygen. So in this substance, I actually already have 4 used up, and I don't want to change the subscript on that substance. So what I'm going to do, I'm going to account for those 4 and take it away so that I'm left with 22 oxygens that I have to balance right here. So in order to get 22 oxygens, I would have to multiply this O2 by 11. All right, if you multiply all this stuff up, it should be balanced at this point. All right, just summarizing everything. So knowledge of the 5 types of reactions is really important. It allows you to predict what the products might be in a chemical change. I think this is kind of a really good cheat sheet for it. So if you have only one reactant, it has to be decomposition. If you have only one product, it has to be synthesis. If I give you an element in a compound, it will be single replacement. If I give you 2 ionic compounds, it will be double replacement. And then finally, if you have a hydrocarbon and oxygen, remember that the products are really easy because it's just CO2 or carbon dioxide and water. Okay, so make sure that if you have any questions you're asking, definitely do the practice worksheets. I know that I give you answer keys a lot of the time, but the expectation is that you are practicing it, you're looking at the errors that you're making, asking questions if you really don't understand something, and then making sure that you don't make the same mistakes over and over again. So have a good day.